So, in this lecture we are going to discuss some more about the diffusion, and in the last two lectures I have introduced the concept of diffusion to you and showed that how mathematically we can deal diffusion in two ways. One, using continuum approach, that is what is normally done using Fick's law, and other one is the atomic scale movement of the atoms. So, let us continue with the continuum approach. The Fick has given a law which describes the flux or the matter passing through a surface at unit time with unit area proportional to the compositional gradient. So, that means we have seen J, if J is the flux, it is proportional to the compositional gradient in the system. In one dimension we can write J is proportional to del C by del X. In 3D this is obviously capital del C. Now, the proportionality constant is always known to be diffusivity or diffusion coefficient. So, delta C is a gradient, obviously that means delta is a gradient operator. Now, this is a fundamental equation in the sense that it relates all the diffusion in the material. This equation is fundamental to any kind of mechanisms we try to explain in the material. So, today using this equation I will show you how we can obtain the flux balance equation, what is known as Fick's second law in the books, but let me clarify, there is no Fick's second law, it is we made the Fick's second law. Fick's second law actually is derived from the Fick's first law, that you will see now. So, before I do that, let me just again tell you that J, at steady state J is defined as a, in a one dimensional case obviously, minus d dc by dx, where x is any location in the medium, and we can actually define in a very simple way. We can assume steady state and isotopic medium, and we can simplify this equation in a very simple way, that is J is equal to minus d del C del x, and that is what you read in the books as a first law of diffusion. And in this equation d is assumed to be constant, and J is so therefore d is basically considered as a scalar quantity. Normally that is not the true, and del C del x is basically, or dc dx is basically treated as a finite form C2 minus C1 divided by x2 minus S1, where compositional variation is shown in this diagram in one dimensional, distances are represented by x and compositions by the C. So, thus we can actually simplify this equation very to the level of our understanding, so that we can use it in any application. And now, let us assume this description of the compositional gradient. I will go back to the board and explain you how the second law can be derived. So, let us assume that I have in one dimensional case in which this is the distance, this is the composition, okay, for any solute. Now, also assume that this is how the composition profile goes by. It can be straight line or it can be curved, does not matter, but for the generality it is, let us assume that this is like a curve. So, therefore, there is a composition gradient, and if I go from one distance to other distance, the composition is reducing. So, if I plot now the J, so J is basically proportional to the slope of this curve, and so therefore slope will be just like a straight line. I can write down these things again. So, this is x1 x2, correct. So, now at x1 the flux is equal to J1, as x2 flux is equal to J2, very clear, right. So, therefore, I can actually do a simple, suppose if I consider and block of material and mark these two positions as x1 x2 again, where this is also x, and let us suppose this surface area of this is A. So, if I assume that the flux coming to this surface at x1 is equal to J1 and flux going on to the surface at x2 is equal to J2. So, we can write down that the mass occupied inside the small volume is basically can be related to del C by del T, obviously in time t, and del T, that is equal to, or let us write down in a differential way, not put the T right now here. The mass occupied is basically equal to J1 minus J2, okay, divided by A, and this must be obviously equal to del T, because the time, the flux multiplied by time into area will be equal to the occupied concentrations in this small part. Okay, that let us suppose this is del x. So, now I can actually write down that del C by del T is equal to J1 minus J2 by dA, correct. So, that is very logically the mass remain in this part in a time of del T can be written like that, and as you know J is nothing but, okay. Now, I can actually do that in terms of the distance. So, there is some mistake here, okay, let us correct it. This must be divided by del x, because we have to consider the distance here. Okay, now, I can do the mass again, so J1 minus J2 divided by del x multiplied by A. So, we can actually write down when del T is or del x are actually small, very small means principally small, we can write down J1 is equal to J2 plus del G del x, right, we can do that. So, if I take back here, then we can write down del C del T is equal to 1 by del x multiplied by del J del x, because J2 will get cancelled, multiplied by area. Okay. So, that means what? If we consider in unit area case, or if we remove the area on this side, we can write down this is equal to del C del x by del J del x, and as you know J is equal to d del C del x in one dimensional case. So, therefore, we can write down these for unit area case is equal to d del C del x. This is for A equal to unit area. So, therefore, if we assume d is an independent quantity, it does not depend on the space and the time, that is always we do, we can say that is equal to d del 2c del x square. That is equal, actually we always term as a Fick's second law, but this is not a second law. As you clearly see, this expression has been derived basically using the concept of J. J is the flux. So, fundamentally I have used this expression J is equal to d multiplied by the concentration gradient. As I am using this expression to derive this final equation, therefore, I cannot say that this is a independent equation, and that is the reason we always say Fick's has given only one law, that is the first law or whatever, it is a law of Fick's law. So, this equation or this expression, especially the last one where we assume d to be independent of the x also t, that means d is a steady state value and it does not depend on the spatial variables, is what we use in the metallurgical community. But for the sake of understanding, it is very clear d need not be a constant as a function of spatial variables. D can be assumed to be constant, or D can be assumed to be independent of time, because we can always assume that D has specific value in the whole system at time t equal to 0 or at time any time, but d can never be assumed to be independent of special variables, and therefore, we cannot take out d from this parenthesis and obtain such a kind of expression. So, basically if you really want to solve this problem, which is the fundamental equation which is required to solve all kinds of diffusion problems in the literature, in the different industrial problems or academic problems, we need not actually take this d out, rather we should do little more maths and try to find out how to solve these problems in a different way. So, if I do that, if I assume d is not completely independent of specific variables, we can write down, we can expand this equation. So, this will be this plus del c del x multiplied by del d del x. Okay. So, that is actually more logically correct expression of the Fick's second law. In this case, you can clearly see we not only need to have compositional the c as a function of x, also we need to have d as a function of x. Okay. The moment we have both these things clear from the experiments, we can solve this c. So, therefore, c, if I have to solve c, or I can write down here c is a function of three things, x, t and d, clear. But in the actual books, or you will see c is a function of x and t. So, the moment you assume c is a function of x and t, this equation is very easy to solve. Why? Because if c is a function of x and t, we can always do the separation of variables and solve these equations. I am not going to solve this equation for in the lecture, it is there in the books, very clearly solutions are given, or you can actually do yourself. You can assume that c is a function of x and t, therefore, you can do the separation of variables. We can always write down this is equal to f of x, f of t, and do the differentiation and separate it out and solve the equation same like a wave equation. Okay. Now, that is one part which you can do yourself, because that is very important, that you must know how to solve this expression. Second part of this is that, let me write down this expression again, the one which is written here, assuming that d is not a constant, is the way it is solved is given like this. Okay, now suppose at a steady state, so this is point number 2, that is the point number 1, please remember these. Point number 2, at steady states, obviously del c del t equal to 0. Steady states means nothing is varying as a function of time, even the composition also. If that is the case, then equation become very easy. It is a correct. So, you can integrate it very easily, and you will find out c will be, let us do that. If I integrate that, what will become? C will be a straight line function, c1 plus d into some x, am I right? c1, so this becomes c1, one integration, then d, okay. This will be like this somehow. There will be two constant because it is a second order differential equation. So, that is also very easy to solve, only we need to find out these functions c1 and c2. Remember, the c1 and c2 will be mostly exponential functions, because in the mathematics you must have read that if such a kind of things has to be solved, actually we can assume this much easily, because it is only dependent on x. So, therefore, there is this will be, the del will become d, it will no longer be del, then it is much easy to solve. So, there are many such different situations are given in the books, and I suggest that you look into it and solve that expressions. Okay, so let me go back into the slides and show you how things are done. Okay, I will just go to directly to this Fick's second law of diffusion. That is what is said. This law is nothing. Fick's first law is not much use on its own unless we know the concentration function of distance. Steady state is basically a special case, remember that. And if we know the concentration of 2 points in a medium along the direction of diffusion, we can calculate easily the flux. To give you an example, let us see the example, then we will get back. Okay, that is better. Let us suppose in case of chemical protective clothings, methylene chloride is commonly used as an ingredient of paints remover. Sometimes what happens, the clothes are attacked by some paints or some kind of a dusts. So, we can use methylene chloride to remove that. Besides being it is a irritant, basically it creates problem on the skin. It may also be absorbed through the skin. So, when using this paint remover, we must use protective gloves, that is mandatorily. But if butyl rubber gloves, which is normally used in the labs, is very small thickness, 0.04 centimeter are used. So, if we use that much thick butyl rubber gloves, then what is the diffusive flux of this hazardous chemical through these gloves? We need to know only the diffusivity d, because d is a constant, it is 110 to the minus 8 centimeter square per second, and very simple, the surface concentration C2 is given as 0.02 gram per centimeter cube, and C1 is basically 0.044. That comes basically from the concentration of the methylene chloride used. Now, we can actually devise the problem in simple way. Suppose this is your paint remover, that is why C1 is there, and this is your glove, which is a definite thickness 0.04 centimeter, and this is C2. C2 is the concentration in the skin, because C2 is the level in the skin which will not create any irritation or any kind of a infection. So, that is 0.02 actually gram per centimeter cube. So, we can write down flux J is equal to minus d del C del x, that is equal to d C2 minus C1 x1 x2, we have seen that, and let us calculate that. Okay, so d is given, C1 C2 are given, and x2 minus x1 is 0.4 centimeter. So, what do you get? You get 1.16 to the minus 5 gram per centimeter square second is the flux. So, that is this number of or moles actually of methylene chloride, which is basically coming to the surface of the skin, and it is not very dangerous. If that is the case, that is the case, it is not very dangerous, because this is very small, very number. So, that is how actually the glove thickness are actually decided. Okay, I am just giving you an example. So, as you let me give you another example, which is more interesting, that if you want to calculate diffusive flux in a during an carburizing experiment. Carburizing I have already explained you in the last lecture. Suppose a plate of iron is exposed to a carburizing atmosphere, and in one side, and decarburizing atmosphere, there is carbon deficient atmosphere on the other side, and temperature is at 700 degrees Celsius temperature. If a condition of steady state is achieved, that means there is no variation of the composition function of time, calculate the diffusive flux of carbon through the plate if the concentration of carbon at position 5 and 10 millimeter, okay, beneath the carburizing surface are 1.2 and 0.8 gram per kg per meter cube respectively, and we can assume diffusivity of carbon is pretty high, because it is the interstitial elements is 3 into the minus 11 meter square per second at this temperature. That is very easy, just to apply Fick's first law. J is basically, as we have seen, d del C del x, and therefore d is 3 to the minus 11, and this C1 is 1.2, C1 is here, and C2 is 0.8, and distance differences are given. So, therefore, we get about 2.4 into the minus 9 kg per meter square per second as the flux. So, Fick's first law is rarely used in the actual explanations, because this only gives you the value of flux, it does not tell you anything else. So, if you really want to know different aspects of that, we need to use Fick's second law, because steady state is basically a special case. Most of our problems are non-steady state, that means it depends on the time. So, therefore, we cannot actually use Fick's first law so much, that is why Fick's second law has been derived from the first law. So, Fick's second law is nothing but a continuity equation, mass balance. We are basically, whatever I have done in this board is basically I have done the mass balance. I have considered two planes and calculate the flux differences, that is nothing but mass balance. The form in which equation is used is in this case is based on the assumption the mass conservation, that is the mass of diffusing entity is neither being created or nor being destroyed. So, that is nothing but continuity equation, and we know the continuity equation is like this. This is nothing but different way of writing Fick's second law, del C del T is equal to divergence of J, and you know gradient is written del J, divergence is written del dot J. Please understand that this is divergence, and we will now make you sure what is divergence. Okay, let us see what is divergence. Now, suppose this is a flow pattern. Suppose something is flowing, water or gas or something, and these arrows indicate direction of flow, and the length of the arrow indicates the magnitude of the flow, velocity, let us suppose. So, suppose if I make a kind of a suppose circle, same diameter ellipse actually here you can see. Now, if I look at it, if I look at these plots, gradient vector field showing three regions 1, 2, 3. Upper one, okay, upper one is basically negative gradient, negative divergence, middle one you see there is no divergence. Why it is so? Because all the arrows are directed in one directions, there is no change of direction of the arrow. So, therefore, there is no divergence of the path is not diverging at all, that is the meaning of divergence. On the top and the bottom you see there is a divergence. On the top you have a change of slope in the negative direction, that is why it is called negative divergence. Here it is positive direction, that is why it is called positive divergence. So, basically you do not need to know what is positive negative divergence, you must know divergence is nothing but deviation of the slope lines. Okay, that is why the divergence comes into picture. So, that means divergence is not the slope, slope can be simply a gradient of the any functions as a function of distance, but divergence is a change of direction of the slope. Okay, now, so therefore, we can write down the continuity equation which I have shown you del C del T, that is del dot J, and J is nothing but d gradient C, and we can put it together and get exactly the same thing what I have done in the board. So, that is del C is equal to d, I know that is the square of del C, and this del square term is known as a Laplacian operator in the mathematics, and it is always denoted by opposite of delta. Okay, it is always denoted in the mathematics. The reason I am talking about mathematics more is because, so these are the things is never discussed in the books, they simply write the equations, but you must know what is meaning of each of these terms very clearly. So, first of all this equation which is the which is rather more correct equation, del C del x equal to del dot d del C, okay, divergence of these parameter d del C is nothing but a second order partial differential equation, obviously, because there is a divergence terms here. We will use the simplified form which is based on the assumption that d is independent of concentration, which is not the true, I told you that. So, therefore, you get this expression when you do that. Remember, although we assume d is not independent of composition, but we never bothered in the actual calculations. We always consider d is independent of composition and solve this differential equation, which is much easy. Now, next comes is that we can write down expression many ways. The best way is writing this way, which is the double derivatives of the C as a function of x, or you can write down this way in a single dimension, when you have a simple case of diffusions in x, we can do that. So, there are some special cases. First special case I already discussed with you, that is the steady state. At steady states the composition as a function of time is 0, and therefore, we get this, and I told you this C is a function of Ax plus b, that is what is written on the class in the board. C2 d multiplied d is also a constant. So, therefore, consternation profile will be just like a straight line as a function of x if the moment you do that. Remember, this is a Poisson equation in the literature, Webb's equation, this is nothing but a Poisson equation. So, Poisson equation solution exactly done the same way. Otherwise, if it is not the case, if it is no longer steady state, then this will be like this, and whenever you have such equations, you have to solve the equations after looking at several assumptions. You can always use infinite medium or semi-infinite medium, okay. and we are going to show whatever time we have in this lecture how we can actually simplify the solution of the equation. That is what I told you. I am not going to solve in that case. Infinite media means what? Diffusion located at on a plane of 0 thickness. Diffusion means the diffusing piece is here. You see, this is medium actually on a plane which is 0 thickness, x is equal to 0. That is, initial distribution is nothing but a delta function. What is delta function? Simple, like this. This is a delta function. That means there is a spike at one position x equal to 0. So, as you go on time, what is happening? It is diffusing both the sides. See here, this fellow is diffusing on the both the sides. As you give more time and infinite time, it will be fully homogenized. So, that is what is known as infinite medium. That means you are assuming the medium is very, very large in dimensions, so that everything can diffuse very nicely. That is the first thing we can do. Analytically, how will you solve this problem? Very simple. You can assume the initial condition x equal 0 is 0, because that is what you assume, but and also at infinity, boundary condition as infinity, it is also 0 for all t. This, remember, the initial condition means only at x equal to 0 C has a finite composition. At any positions other than that, C is 0. That is the initial condition. That is what is known as delta function. So, and you will get this is the solution finally if you do that. That is nothing but error function solution. What you are doing is basically m divided by 2 root pi dt exponential x square by 4 dt. X square by 4 dt is basically a exponential term here, and that value has to be calculated and separately. If you plot that solution, that is your x equal to 0, there is a spike here at, okay, you see here, then slowly the spike is getting reduced as you see this is dt equal to 0, that means t is equal to 0, t equal to 0.025, that is dt is equal to 0.025, dt equal to 0.5, dt equal to 0.75, dt equal to 0.25 and 3. So, when dt is very large or time is infinite, it has become homogeneous all throughout, that is the idea. So, this plots actually Gaussian type, because this equation is Gaussian. You see here, this is a Gaussian equation. These are all taught in details in diffusion. Now, okay, this is the best way. Otherwise, you can always assume a semi-infinite medium and solve the same equation. You will get again this solution. That is what is known as error function solution. Okay, so we will you must read it carefully, because as a part of assignments there will be problems based on these equations, and you must know how to solve this equation very easily. Please practice yourself, otherwise you will not be able to do yourself. Practicing these mathematical equations requires some time. In case you do not understand it very clearly, or you have problems in even mathematically dealing the equations, please get back to us. We will put up some more notes so that you can understand that. Okay, so in the next lecture, I am going to talk about how diffusivity varies with time, temperature, because temperature has a strong role to play in deciding the variation of diffusivity, because diffusivity D is a very important parameter. It comes in all solutions. So, diffusivity must be known. As I told you in the lecture that we always assume diffusivity independent of the spatial variables. That is also not correct. If you really want to know how we can solve the equations in which diffusivity is not assumed to be independent of spatial variables, then it is a separate discussion that requires we to deal the problems in a separate manner. It is there in the books. Actually, Motano first time solved the problem in assuming a plane, zero flux plane. But we are not going to deal it here, because that is a separate issue which may not be required in the phase transformations. Okay, so in the next class we will discuss about the temperature dependent diffusivity.